Okay, folks, I'd like to look at a example problem from section 16.4 that we didn't finish out last time. So let's go ahead and work through this. The goal is to find the volume of a particular shape that's bounded by the first octant and these two planes here. So we'll sketch the shape in just a minute, but I just want to remind us that if we're looking for the volume of a shape, we can accomplish that many different ways. We could try to do this as a double integral and then for some function f of x, y, dA. We could try to do it that way if we had a function that described the upper part of that shape, or we could, maybe transform it into a different integral where we're thinking of it maybe an integral over some region d of maybe f of in this case maybe something like f of x z dA. So maybe this would be a region in the xy plane, where this would be a region in the xz plane. Or we could even try to do it as a double integral this way, where we'd have maybe some y comma z as a function dA, and this would be a region in the yz plane. So all of those will work. We could do that for, we could make the integral work that way. But the way we're going to do it in this problem is the triple integral way, where we're going to take the triple integral over some other region R, where this is in the xyz plane, or xyz space here. And we're going to take that of our area finding function 1 dv. So although we could have accomplished this problem in earlier sections, we're going to go ahead and use this triple integral format here. So let's go ahead and try to sketch this region. I'll do my best here. In the so here we've got the x plane the x coordinate system, the y coordinate. So here we've got the xy plane, and we've got this one plane that we're going to be dealing with. This is a plane in 3 space, but to help draw it, we notice it doesn't depend on z, so it's going to be it's going to have the same level curves for any choice of z value. So I'm going to go ahead and just sketch it in the xy plane now. So let's see here. This says if we go out, let's see, when x is 0, we could go up 4 units on the y direction, and this will have a x-intercept at 0, 2, and so here is a line connecting those 2 points. That's the line here, and what I'm going to think of then is the plane, which I'll sketch in green, which encompasses that line. Okay, so this is the plane, y equals 4 minus 2x. Okay. Also in our system we have the plane z equals 6. So there's let's go up 6 here. So 1, 2, 3, 4, 5, 6. So here is the plane where z is equal to 6. So this is the plane where z is equal to 6. And then the fact that we're in the first quadrant, or first octant, I mean, restricts us to, we need to be above the xy plane. We need to be in the positive y direction of the xz plane, and in the positive x direction of the zy plane. So that's quite a mess. What I recommend then doing is let's go ahead and resketch this. Again, we'll put it in the xyz plane, but we'll be able to draw it a little bit more nicely now. And here we can see this prism that was referenced in the problem. So here's the z-axis, the x-axis, and the y-axis. So now again, folks, there's lots of other ways we could compute the volume of the shape. I mean, frankly, you don't even need calculus for this if you just do a little bit of thinking. You could compute the volume of the solid by finding the volume of the corresponding rectangular or parallel pipette and then cut it into half. But we're trying to use calculus here, so let's go ahead and do that. So what I'd like to do is I'd like to sketch what this looks like in the xz plane. Okay, so that is, I'm looking at this plane right here, and I want to look at what this, what we would be doing is we pick x coordinates and z coordinates. So we said that the x coordinates need to run between 0 and 2. So there's x equals 0, there's x equals 2, and then the z coordinates are going to run up to 6. And so this is what our domain space of if we want to think of this as an area function. That's where our domain space would be coming from, and then we would be selecting an xz ordered pair from within there, and we would plug that xz ordered pair into the function to find the corresponding height y value. So it's not really height, but how far we go out on in the y direction. So another way to look at that here is that we've got, here's, let's be careful with the orientation. Here's x, here's z, and we're taking from this domain region right here. So let's go ahead and label that. We'll go ahead and label that D here. Let's see here, what letter are we using? We'll use D because when I think about it in the 2-plane. And then here is, so here's our y, and here is that line that we sketched before. So here's where y is 4. So here's that line that we sketched before. And so here we have, you know, another viewpoint of this surface where we think of plugging in the ordered pair x comma y, and then it will, or excuse me, x comma z, and then it will spit out the y coordinate, which is given by 4 minus 2x. So that's how we're setting this up. So now we're ready to go ahead and think of, okay, just like we did previously, we'll fix a y, or we'll fix a z coordinate, and that's going to restrict us to some line here. And then we'll pick some x coordinate from in there. That'll put us at some point along that line, and then we'll plug that into the function, and that'll give us the, I should really do that in a different color. Let's do that in, I guess, orange here. That'll give us some z coordinate, right? So as we're setting this up, I'm going to try to do these as color-coded integrals here. So we're going to integrate, and I'm choosing to integrate this last with respect to z, and then with respect to x, and then with respect to y. So there are other ways you could set this up. Of the 6 possible iterated integrals, I believe 3 of them will work. But anyway, we see that our y values are going to work from y equals 0 all the way up to where we hit this curve, and we hit that curve when y is equal to 4 minus 2x. So we hit that upper part of the surface. So this is where drawing these pictures can be a little bit helpful. We're going to think of choosing y values all the way in between here. We'll start at the y value of 0, and we'll stop when we hit the ceiling, if you will, of this solid space. Okay? Of our function, well, we're just doing the volume function, so that's dy. And I guess there's no reason to color code that. We'll just keep that black. And then what were our x coordinates doing? So that was, you know, for a fixed z coordinate, we were taking different x coordinates. They were ranging between x equals 0 and x equals 2. So again, folks, where this could be maybe some other curve, we could have had, instead of that being the fixed number 2, that could have been some function involving z there. And that's why certainly these 2 integrals are interchangeable. And then our z coordinates, they are running from z equals 0 to z equals 6. Okay? So I hope that this helped a little bit to see how, when I color-coded this, that we first fix a z value. For a fixed z value, we then integrate all the way through x. So we would integrate all the way along this red line here for a fixed z value. And then for each one of those x values, if we were to fix one of them, we would then integrate all the way along the y value that corresponds to that fixed z and that fixed x. Okay, so then the last integral, folks, I meant to put a 1 there. And so then let's go ahead and finish out putting in our, so dy, or dx, and then dz. So folks, pause the video and try to integrate this, and I'll go ahead and write out the solution and show it to you here after you've paused the video. So folks, I went ahead and integrated this function first with respect to y, which gave us, you know, the integral of 1 with respect to y just gave us y. We evaluated at these upper and lower limits of integration, and then we integrated, that gave us the function in terms of x, which we then evaluated with respect to x. We plugged in the limits of integration for x, which gave us the number 4. We integrated 4 with respect to z, and we went ahead and evaluated it. So take a look at that. Let me know if you have any questions over that. I think the color coding might be helpful. Okay, and again, that color coding went with our original choice here, where we said, okay, we'll start off by fixing a z value, and then we'll integrate along this line right here. And let me go So we fixed a z value, we integrated along this line here, and at each point we would take an x-coordinate from that. So if we fix one x-coordinate, we'd have that point right there, and then we integrated along the z. So the innermost integral then is that, once we fixed a z and we fixed an x, we then integrate all along z. That gave us the innermost integral. So anyway, just look over that. Let me know if you have any questions. You can pause the video there or whatever. And then I just want to show you there are many other iterated integrals we can and cannot do. So the first two that I've given you will not work. These are the two iterated integrals of the 6 that will not work in this particular problem. And I think that's clear, right? You can't have a function of x on your outermost iterated integral. But for example, here this would be an example of one that would work, and if you were to evaluate this again, you would also get our answer of 24. I encourage you to do this iterated integral. It's not too challenging at all. It's about as easy as they come. Do that and confirm that you get the same answer that we got before. All right, folks, I hope this video was helpful. Thank you.